All right, one more last little quick example before bedtime here. You got a rubber ball of mass m. It's dropped off a cliff. As it falls, it's subject to air drag. The drag force has a magnitude of bv squared. It says magnitude there, kids. Where b is a constant and v is the instantaneous speed of the ball. And the drag coefficient is proportional to blah, 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 blah. As the ball falls, its speed approaches a constant value called the terminal speed. So on the figure below, draw and label all the forces on the ball at some instant before it reaches its terminal speed. It's really important there. It says at some instant before it reaches its terminal speed. It's not saying immediately after it's dropped. So that implies it's been in motion for a little bit, and so it's going to have some non-zero velocity. On the test, you want to draw it on the dot, but there's not a lot of space over there. So I'm going to make my own dot over here, and I'm going to show the gravitational force, mg, and then I'm going to make an arrow here for the drag force, and I could call it F drag, but I'm just going to call it BV squared. And I'm drawing it in such a way that this arrow is clearly shorter than that arrow. I don't want that to be ambiguous there because it has not reached its terminal speed. So those forces aren't balanced. At terminal speed, you're no longer accelerating because the drag force is balancing out the gravitational force. You have no FU, so you have no acceleration. All right. State whether the magnitude of the acceleration of the ball increases, decreases, or remains the same as the ball approaches terminal speed. So again, as this thing keeps falling and velocity gets bigger, this force is going to get bigger, 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 bigger until it matches this thing and we no longer increase velocity. So what's going to happen in the acceleration? The acceleration is going to be getting smaller because the FU is getting smaller. So for B, acceleration decreases because as velocity increases, F drag increases, reducing balance force, but here we're going to use the AP wording, reducing the net force and therefore the acceleration. Okay, so it says explain, so you've got to have a few links in the chain there explaining why your answer is correct. All right. Right, but do not solve a differential equation for the instantaneous speed of the ball in terms of time t, given quantities and fundamental constants. So this sounds really scary, right? Especially to the non-calc kids. But it doesn't end up being that scary. Okay, so recall that Fu equals ma, and this is almost always how this sets up. That unbalanced force is going to be the difference between mg and bv squared. Okay, that's going to equal ma. I want to set this up for a. That's this whole bit about the differential equation. So I'm going to divide both sides by m. So mg minus bv squared, all that over m equals a. And so the whole differential equation bit is just recalling that a is dv dt. Okay? And then I'm going to simplify this thing a little bit. Mg over m minus bv squared over m. So this is going to become g minus bv squared over m equals dv dt. Okay, and that's literally all the farther you need to take that here. So we're setting up, but not solving the differential equation for the instantaneous speed of the ball. And then the last bit is wanting us to find the terminal velocity. And so the terminal velocity occurs when mg minus bv squared equals 0. Okay. So then mg equals bv squared, and I want the terminal velocity. I probably should be subscripting this because this is specifically at terminal velocity. This is 0. And so at terminal velocity, these things are equal. And then I just solve for the terminal velocity. So vt squared equals mg divided by b. And yeah, you don't have to write out all these steps, but I really like algebra. So there it is. That's the terminal velocity. And that's all we had to do there. We didn't really have to get very calcy with a drag force problem. So be aware of that. Just because you see a drag problem on exam day, don't wave the white flag. Try to find all the points that you can get. And you might get pretty far into it and realize you really have to pull out of calculus, which if you're a pre-calc kid, hey man, that's a win.